All right, welcome to the Explainer. Today we're going to dive into something that sounds like a total paradox. How do you find any kind of order in complete randomness? We're going to see how digital signal processing gives us this incredible statistical toolkit to find patterns hidden in what looks like pure, useless chaos.
Okay, so first things first, let's get a handle on what we're even talking about. In a perfect world, in a textbook, you get signals like the one on the left. It's clean, it's predictable, you know exactly what it's going to do next. But reality? Reality is the signal on the right. It's messy, it's full of these random jitters and fluctuations. I mean, this is the hiss you hear on an old tape, it's the static on your car radio, it's all that noisy data coming back from a satellite. These are random signals.
So right away, you hit this massive wall, right? If a signal has no rhyme or reason, no predictable pattern, what can you possibly do with it? How in the world do you filter out noise when you can't even define what the noise is? And how could you ever predict what's coming next if it just looks like chaos? Well, the answer, and this is where things get really clever, is to completely flip how we look at the problem. Instead of getting bogged down trying to define one specific messy signal, we use statistics. We start treating the signal as a random process. Basically, we look at the entire universe of possible signals it could be, and we describe its overall character. So the first tool in our statistical toolbox is something you're probably familiar with, the mean. It's really just the signal's average value over time. You can think of it as its DC value, or its baseline. It's the center of gravity that all those random fluctuations are happening around. Okay, now we're getting to a really cool idea. It's called autocorrelation. The best way to think of it is as a signal's memory. It basically asks a really simple question. If I know what the signal's doing right this second, how much does that help me guess what it's going to do in the next split second? If that autocorrelation is high, the signal has a strong memory. Its past is a really good predictor of its immediate future. And trust me, this idea is absolutely crucial. And that brings us to maybe the most important tool of all, the power density spectrum. Just think of this as the signal's unique fingerprint, but for frequencies. It takes all that chaotic, messy energy and tells us exactly where it's all going. It shows us, plain as day, which frequencies are strong and loud and which ones are barely there. And this is the light bulb moment, right? Once we have these statistical descriptions, especially that power spectrum, that fingerprint, we can actually start to tame the randomness. We can now design tools to shape and manipulate that signal in incredibly precise ways. So let's take a classic example to see how this works. Think about white noise. You've heard of it. Well, its power spectrum, its frequency fingerprint, is totally flat. What that means is it has the same amount of power at every single frequency. It's the ultimate random jumble, which actually makes it the perfect canvas for us to work on. All right, so how do we actually do anything with this noise? Well, we use something called a digital filter. And honestly, the best way to think about a filter is like a stencil. We get to design its shape. This particular stencil here is a low-pass filter. See how it has big openings on the left for the low frequencies to get through, but it pretty much blocks all the high frequencies on the right. And here's where the magic really happens. And it's all down to this surprisingly simple math. The fingerprint of our final output signal is just the fingerprints of our original noisy signal multiplied by the shape of our filter's stencil. That's it. We're literally reshaping randomness with simple multiplication. We take the flat fingerprint of the noise, press our stencil down on it, and we get a completely new fingerprint. And boom, look at the result. We've applied our low-pass stencil to the flat fingerprint of white noise. Now the output signal is still random, but its entire character, its personality has been transformed. All of its power is now bunched up in the low frequencies because we've totally carved out all that high-frequency noise. And look, this isn't just some abstract idea. This is the engine behind so many things we use every day. By understanding the statistics of noise and designing the right filter, we can get rid of that annoying hiss from an old recording. Or, as a quote from our source material, Random Processes in Digital Signal Processing, points out, we can even build systems to get rid of echoes. Okay, cleaning up noise is cool. It's super useful, but what if we could do something even wilder? What if we wanted to actually predict the future of a random signal? Remember when we talked about autocorrelation? That idea of a signal's memory? Well, this is where it pays off, big time. If a signal's past is connected to its future, if it has memory, we can totally exploit that.
We can look at its recent history to make a really, really good, educated guess about what it's going to do next.
This amazing technique is known as linear prediction. What it does is build a custom-made filter that's constantly analyzing the signal's recent past to make the best possible guess about its very next value. And this isn't science fiction. It's the core technology that makes speech coding work on your phone, and it's even used in things like financial market analysis.
Okay, let's pull back for a second and just think about what we've covered. Why does any of this really matter? Why is looking at signals this way so powerful?
Think about the journey we just took. We started out with this mess, right? These totally unpredictable signals that are everywhere in our world. But by putting on our statistical glasses, we found a way to describe them, using tools like the mean, autocorrelation, and that all-important power spectrum. And once we had that description, that became a roadmap for building powerful digital filters to clean up, reshape, and even predict these signals.
So the big idea here, the one thing to remember, is this. What looks like pure, useless noise can actually be turned into incredibly valuable information. The absolute heart of modern digital signal processing is this ability to look at a whole mess of possibilities, find the hidden statistical structure, and then use it to our advantage.
And that kind of leaves us with this really big, fascinating question, doesn't it? We've figured out how to find predictable patterns hidden deep inside random signals. So what other chaotic systems in our world, from the stock market to weather patterns, aren't really random at all? Maybe they're just waiting for us to find the right filter to finally make sense of them.